Hello folks, I'm Kjell Fritz and I would like to discuss with you an explanation that I have discovered for the Meissner effect using classical physics only. And this is based on the phenomena which we call electromagnetic induction. And I will formulate this phenomena through the inductive force, which is also called the Weber force. And then I will explain what it is, Meissner effect, it's magnetic levitation. I will present a model, and then I will apply the Weber force on magnetic levitation. This is a work that was published 3 years ago, and it is open access. This is the basic electromagnetic induction. We connect a conductor to a battery and then the electrons are accelerated, and during acceleration they experience an opposing force. And this force we call the inductive force. It is due to the acceleration of all the other electrons. This inductive force is the origin of inductance, and it is also the source of magnetic energy, because the inductive force, that is the one that has to be overcome by the electrons when they are accelerated to establish the current. To simplify maximally, we look at the process for two interacting charges only. So if charge 1 is accelerated upwards, then charge 2 is influenced by a force downwards, so in the opposite direction. This is the inductive force. And to describe the measured and observed phenomena, which of course are plenty, Weber found that one can formulate this with one and only one force between the two charges. Later on, Moon and Spencer during 1950s, they reformulated Weber's formulation in this way, which is more appropriate for our purpose during this presentation. So we see here the product of charges. So they have the, let's assume these are two electrons, so they have the same charge, but this formula is also valid for oppositely charged particles. We have distance between the charges here, r, so it's 1 over distance dependent, not 1 over distance squared as usually for forces. And here we have the acceleration of charge number 1, so this is the force on charge number 2. We have speed of light here, c, and we have permittivity epsilon 0. There's a minus sign now, because this will give a desired direction of the inductive force. But if they are oppositely charged, then the inductive force will be in the same direction as the acceleration. So we go now to the Meissner effect, and we will model it in a proper way, so it will be easy to apply the Weber force. What is the Meissner effect? Well, a permanent magnet is resting on a material. This material has then a temperature which is decreased until the material becomes superconductive. At that moment, the magnet levitates. So a repulsive force appears. Now, you may have seen movies on this, and you have to distinguish this phenomena with another closely related, and that is when the case where the material is made superconductive and then you introduce the magnet towards the material. This is different. This is not the Meissner effect. So the magnet has to be resting on the material before it becomes superconductive. So this repulsive force is magnetic. That is clear. It's a magnetic interaction. This permanent magnet we can picture as a coil. So it comes in with a certain current when it is resting on the material. So the thing is that the material, when it becomes superconductive, must respond with a current which is oppositely directed that of the current of the permanent magnet, that is the coil. Because oppositely directed currents, they repel. So that's the only way to get a repulsive force. There are two possible orientation of the magnets illustrated in these two figures. There's the same argument, same reasoning for the two cases. So I will focus on the left one, which is a bit easier. So the thing now is just to find an explanation for why the superconducting material generate a current which is oppositely directed that of the current of the coil. So we do this in 3 steps. We will apply the Weber force. So here in blue we have the material which will become superconducting. In black, that's the permanent magnet which will replace by a coil. And this coil can be maximally simplified by being replaced by a single loop only, single current carrying loop. Here we see the current direction of this loop. It is counterclockwise. Now, this means that the electrons of the loop will experience a centripetal force, which gives an acceleration AC. Now, so although this loop maintain a constant current, there is an acceleration. It's a centripetal acceleration. So that acceleration will influence all the other charges, in particular those charges of the superconducting material. That will give a force in the opposite direction to the influence, according to Weber's force. So we can go back, look at the Weber formula. This is the basic phenomena that we apply. Acceleration gives an oppositely directed force for same sign charges. That's what we deal with now. Those are only electrons. So electrons of the superconducting material will be affected by a force which causes an acceleration in the opposite direction. So that is radially outwards. And that I have denoted AW, W for Weber. This is the Weber force causing this acceleration. And I write acceleration now instead of force to emphasize that the motion is created. The material is superconductive, so it doesn't matter how small the Weber force is. Any minute influence of electrons of a superconductive material will cause an acceleration and a motion of the electrons of the superconductive material. So a current is built up, and this is directed radially outwards. Now the third step here, this figure, during this motion of the electrons radially outwards, they are influenced by a magnetic field, a field from the coil. So this will cause a magnetic force, which is usually called the Lorentz force. So that's why I have an index L here. So that Lorentz force is directed perpendicular to the Weber force. This will cause a creation of a circulating current in the direction of the red arrows. This circulation is then clockwise. So this causes a current which is oppositely directed the current of the coil, which was counterclockwise. So that is the proof of that a repulsive force is generated because we have two currents in opposite direction giving a repulsive magnetic force. And the current generated in the superconducting material will be so large, it will be large enough because the electrons are accelerated without any resistance. So currents will be large enough until repulsion appears, and then when distance increase, the influence decrease, and the interaction stabilizes, so balance will be reached. So this is a very nice physics exploration because we don't need any calculation. Because of the superconductive material, the current will be strong enough in order to establish this repulsive force. So this is a conceptual reasoning leading to an explanation of the Meissner effect within classical physics using the electromagnetic inductive force, which we call the Weber force. So that is the conclusion of this work, that it is quite possible to explain Meissner effect within classical physics. And this is, has been debated vastly in the literature. And there are many models of the Meissner effect, most of them based on quantum mechanics. But this is one model based on classical physics solely. Thank you very much for listening, and if you're interested in this, feel welcome to contact me and we can discuss further. Thank you very much.